Hello students, this is Professor Chalai, and in this video we're going to look at some of the things you need to know for your gas productions lab. Let's get started. So in this lab we'll react solid magnesium with hydrochloric acid, aqueous hydrochloric acid. And this is a single displacement reaction. It's a redox reaction that produces hydrogen gas and magnesium chloride salt. Now, to balance this equation, we need 2 hydrochloric acid to balance this equation. We're producing gas. Now, we know that if we look at the ideal gas law, PV is equal to nRT, as we produce more and more hydrogen gas, the number of moles of hydrogen will go up, which means that the other variables in this equation, the pressure, volume, and temperature, could also change. So if we want to monitor the gas being produced, we'll have to keep 2 of those 3 variables that could change constant. How do we do that? Well, let's try to keep volume constant by making sure that whatever gas we produce gets trapped in a container with a known volume, like an Erlenmeyer flask. So what if we perform a reaction in here that produces our gas? The gas is trapped in this volume, so we can keep that volume fixed. We can also keep the temperature fixed by making sure that this entire reaction is done under some conditions where we can monitor the temperature. For example, like in a water bath. So let's do that, water bath, where we can stick a thermometer in here and monitor the temperature constantly, right? A little temperature sensor, a temperature probe. That way we can keep temperature fixed. What does that mean? Well, it means that as this reaction proceeds, in the beginning there'll be 0 moles of H2, and as the reaction proceeds we'll create more and more moles of H2, the pressure will go up, right? These two are directly related. So we can actually directly keep track of how many moles we produce by keeping track of the pressure of the gases from a reaction. And this is the essence of the lab we're going to do. We're going to be producing some hydrogen gas, we're going to keep volume fixed, temperature fixed, and we're going to keep track of the pressure to monitor the reaction. Now, how are we going to set this all up? Well, let's take a closer look at this, just the flask here in this setup. So we'll have a flask, right? You'll have to make sure it's tightly stoppered inside of a water bath, as I mentioned, with a little piece of metal right there, or magnesium metal, and this will be connected to our pressure sensor. We'll also have a little syringe here that we can inject air or anything else into the flask as needed. And we'll have our little pressure readout on our screen. We'll have pressure, and we'll see how pressure changes with time. So initially, if you do nothing, right, the pressure should be relatively stable. And then in this syringe, you'll have the hydrochloric acid. So here, this is going to be your magnesium, and in here, you're going to have your hydrochloric acid, your aqueous hydrochloric acid. So you're going to inject your hydrochloric acid by pressing down on a syringe such that, it enters in here, and that'll start the reaction. Now, because you've pressed down on the syringe, you're actually adding stuff in here. What you'll see from our pressure here is a spike, right? We don't really want that spike, so what you'll do after you push down on the syringe to add the hydrochloric acid, you'll pull back out the syringe so that that spike goes away, and you'll have something like that. So you'll have your hydrochloric acid mixed with your magnesium metal. And as they react, the pressure will slowly increase, because as they react, it's going to create hydrogen gas, H2 gas, until all of the magnesium is completely reacted, in which case you won't produce any new gas at all. And so you'll have a flat line there. So this initial part here, that's your initial temperature. This is your final temperature. Sorry, not temperature. That'll be your initial pressure and your final pressure to give you your pressure change, your delta P, if you will. So that's it. That's the essence of the reaction. We're basically reacting hydrochloric acid and magnesium, finding the pressure change. Now that pressure change is interesting because before you add anything in there, the pressure that you would have had here, that's your atmospheric pressure, right? It should be close to 1 atmosphere. But after you've injected the hydrochloric acid and your metal, this increase in pressure, right, that pressure change is due to two things. Not just it's due to the hydrogen gas that's produced in the reaction, but it's also due to water vapor. Because remember, HCl aqueous is dissolved in water, so now you have water in here, and so whenever you have water in equilibrium with air, there'll be some vapor pressure. So let's say your pressure difference here was, I don't know, 0.056 atmospheres. That's your pressure difference. That pressure difference, that total pressure, comes from the pressure of our hydrogen plus the pressure from our vapor pressure of water. If your water bath was, let's say, 395 kelvins, I'm making up some numbers, then the vapor pressure of water, you'll look up in a table, and you'll see that that vapor pressure, so vapor pressure of water at 395, sorry, let's do 295 kelvins. 295 is very hot, over boiling. So let's say it's at 295 kelvins. That vapor pressure, if you look it up, you'll see it's 19.8 millimeters of mercury. If you convert that, that's 0.026 atmospheres. So basically 0.026 atmospheres of this total 0.056 atmospheres comes from the vapor pressure of water, which means the vapor pressure of just the hydrogen, which is what we really want, is going to be our total pressure, our total change in pressure, minus our vapor pressure of water, which in this example gives us 0.030 atmospheres. That's our partial pressure of hydrogen gas produced from the reaction. Okay, so we now know the amount of pressure due to our hydrogen that we created from this reaction, but how many number of moles that is? Well, we can easily figure that out. So this is going to be our experimental number of moles. This is the number of moles that we obtained from our experimental calculations. So we know that the pressure of hydrogen times the volume is equal to the number of moles of hydrogen times R times T. We know V, or we should know V, we should know T, R is a constant, and we just figured out what our partial pressure of hydrogen is. So our number of moles of hydrogen should be the partial pressure of hydrogen times the volume divided by R times T. We said, suppose in this reaction it was done 295 kelvins. What if the volume that you found for the little container here that I said we were using to constrain the volume, what if that volume was, let's say, 200 mils, which is 0.200 liters? If that is our volume, then we can easily go about finding the number of moles here. So the number of moles of our hydrogen gas is going to be equal to our partial pressure, 0.030 atmospheres, times our volume, let's say that was 0.200 liters. The ideal gas constant is 0.08206 liters times atmospheres over moles times Kelvin, and our temperature we said was 295 kelvins. Again, these numbers, except for the ideal gas constant, these numbers will depend on your particular experiment. But you plug all of those numbers in a calculator and you should get a number of moles according to this of 0.00025 moles, right? This is your experimental yield. This is the number of moles of hydrogen you would have produced from your experimental setup. Now, I said we choose some amount of metal, but in your lab, you're going to be choosing a specific amount of metal, somewhere between 0.010 to 0.020 grams of magnesium, right? So theoretically, that should give you a specific amount of moles of hydrogen gas produced. So let's say for our example, we use 0.010 grams of magnesium, right? According to the balanced chemical reaction, 1 mole of magnesium will react with 2 moles of hydrochloric acid to produce 1 mole of H2 gas and magnesium chloride, 1 mole of magnesium chloride, right? So if we figure out the number of moles of magnesium, we should know the number of moles of our hydrochloric gas. So the molar mass of magnesium, if you look it up on the periodic table, is 24.31 grams per mole, which means that our 0.010 grams of magnesium can be used to find moles of magnesium, right? And then that could be used to find moles of hydrogen gas, because 1 mole of magnesium gives us 1 mole of hydrogen gas. So if I plug this in my calculator, I should have obtained 0.0040 moles of hydrogen gas. And so that's our theoretical yield. So that's it for calculations, right? So to summarize, we're doing a reaction that produces a gas. In this case, it's a single displacement or redox reaction, where magnesium reacts with hydrochloric acid to produce hydrogen gas and magnesium chloride. Because the number of moles of hydrogen will be increasing as this reaction continues, we want to keep track of it. And we wanted to keep track of it through the ideal gas equation. But to do that, we need to keep a couple of variables fixed. We'll keep volume fixed by making sure none of the gas escapes. We'll keep temperature fixed by keeping all of this in a water bath. But you'll need to know exactly what the volume is of the container. You'll need to know exactly what the water bath temperature is. Note, I want to point out here, the volume of their flask is not the readings that you see on the side of the flask, because that don't account for the extra air that you would see on the top. So you need to figure out exactly what the volume of that flask is. And then once you have that set up, as the mole increase, then the pressure should increase, which you can keep track of using our pressure probe. Also, I want to point out that this whole setup only works if no gas escapes. So you have to make sure everything here is nice and sealed. The cork is nice and tightly sealed. The pressure probe, when it goes in, doesn't cause any air leakage. And then the syringe that you're going to have here, this syringe that you're going to inject the hydrochloric acid with, that doesn't cause any air to leak as well. With that, make sure you pull out back the syringe so that your initial pressure doesn't starts at the point you expect it to start. You don't have the spike, and then you can keep track of the moles produced by just looking at the pressure change. When it's stabilized and all of the magnesium is used up, you know that the reaction is complete. When you're looking at to figure out what the partial pressure of hydrogen is, you have to make sure that you subtract out the partial pressure of water. All right, if you have any more questions, you can always reach out to your instructor and always have fun in lab.